wrong as a Sagan workshop feels like. I want everyone to just stand up, shake it out for 5 seconds. I'm going to count down and then sit down. All right, shake it out. 3, 2, 1, sit down. Okay, awesome. Okay, so I was tasked today with overviewing current and future exoplanet populations. All right, so this could actually be an entire Sagan workshop in and of itself. In fact, there was one on planet populations just 3 years ago. There's no way that I'm going to be able to put a week's worth of lectures into 45 minutes. So I'm not even going to try. All right, so what I decided to do with this talk, instead of just running through a whole bunch of population results, by the way, you've heard some of these throughout the week already, what I'm going to be talking about in my 40-ish minutes is the things that if you're interested in doing population analyses, you really should be thinking about, okay? So this is a general talk about what you need to be doing if you are going to be doing population analysis. So because the theme of this week is there really a planet in my data, another way of thinking about this talk is there really a population trend in my data set? I can tell you that a lot of people have gotten fouled up by not considering the things that I'm going to be talking about today. And they've claimed population trends that weren't there. Don't be that person in the future. Okay, so before I go on, I just want to spend a little bit of time talking about why exoplanet populations. Is this the forward? The F is forward, okay. Why planet populations? Why do we even care about them, right? I understand the glory of finding the smallest, most habitable exoplanet. Why would we instead take a statistical approach? Okay, well, first of all, as physicists, we want to understand how planets form and evolve, all right? So this is an enormous industry of people working on this right now. Part of the complexity of this is that many physical processes are at work at the same time. So accretion onto the star while also accretion onto the planets. There's migration of both the planets almost fully formed within the disk, but also material that will eventually become planets in the disk. There's photoevaporation after the planets have been formed. And some of these processes are actually stochastic. So if you input one set of parameters, you will get a distribution of outcomes, okay? So we need more than just one system in order to be able to understand this process of planet formation. And this one system that I'm referring to here that we need more than is our solar system. So what we want to be able to do, instead of just understanding and crafting a story for how our solar system formed, we want to understand how these kind of physical processes can produce this broad range of system architectures and planetary properties that we are really starting to get a handle on now. Okay, the final kind of note here is that we've been really surprised by exoplanets before. The existence of hot Jupiters, that really surprised people. And then shortly after Kepler was launched and started kind of teasing us with first results, just the plethora of sub-Neptune super-Earth planets. We had no real expectation that there were going to be that many planets between the size of Earth and the size of Neptune based on our own solar system. So we've been surprised twice in 2 decades. We're not going to stop being surprised. We really need to understand and we need to map out the full diversity of extrasolar systems here. Okay, so this is kind of like a meta note here. On the kind of theory side, which I'm not going to talk about at all, but I wanted to mention, the kind of study of planet populations is done with planet population synthesis. So you can understand this as a simulation of many exoplanet systems based on the physics that we understand. So there are several groups working on this. This plot is from Christoph Morosini's work doing this. All of these, so in particular, we're looking at the mass of the planet and the radius of the planet. I tend to think a lot in this space. My work is in mass and radius stuff. So what he is showing is that he is simulating using things like planet migration, certain prescriptions for accretion, that he is producing planets in a specific locus of mass and radius space. This is a testable prediction. So what we want to do is test and compare the output of these kind of population simulations to what we actually observe. Of course, there's a whole lot of tunable parameters that go into this as well. So that is something that you have to keep in mind when you are comparing data to theory. But this is part of what we want to better understand, is all of these tunable parameters that go into it. Okay. Right, so comparing these to observed populations test theory. All right, so what is actually observed? All right, so I went to exoplanets.org to get this plot real quick, really late last night. So what we're plotting here is semi-major axis, so distance between the planet and the star, and then the planet's mass here. The color bar is the mass of the host star. All right, so it is really tempting when you're first starting out in population analysis to do exactly what I just did and make this plot and compare what you get here with your the output of your theoretical simulations. All right, so let's just do this extremely naive thing. All right, so what features do you see in this plot? This is where this plot becomes interactive. So speak up. What features do you see in this observed plot? Okay, yeah, that's one of the first things that I noticed too. Any other features? Yep. Okay, I'm just realizing I need to repeat this for the people who are watching online. So the first point was that we have 3 different kind of clusters of planets, and your point is the desert. Here. Is that what you're talking about? Yeah, so there seems to be a desert here, so it's kind of related to the clustering. Yeah. Yeah. So that is also something that you can see from this plot. So the more red points means that those planets are around more massive stars. And the points on the top of the plot, some more massive planets, are also around more massive stars. So there seems to be some sort of trend there. Yeah? Yeah, so the black points are, for whatever reason, the exoplanets.org is not populated with a stellar mass, whatever reason. Any other trends? Yeah.
Literally, there's no other Earth analog.
Yeah, okay. So if we want to look at Earth, which is right where that W is, there are really no other planets around there. All right, so that's definitely a feature of this. You might also be tempted to think, there's an interesting trend here, where planets that are farther from their stars might be more massive, okay? These are all things that you can take away from this plot, and you will be misled by doing this, okay? So how exactly are you going to be misled by just taking a look at this plot? Okay, first, part of our job of scientists, actually a large part of our job, is not only do we want to put points on this plot, find these planets and measure their properties, we also really need to understand how well we measure those properties. That's an enormous part of our job. And so I have not plotted any error bars here. When you do that, then you can start seeing the kind of the quality, the level of our understanding of the points on this plot just to begin with, okay? So you can notice that there seem to be not very large error bars up here, all right? And then as you go down in mass, these error bars start to become very large, okay? So a lot of the structure that you might think that you see here might actually be due to measurement error, okay? Next thing, which planets are missing? So this is thinking about what's not even on this plot, all right? So as you go smaller in mass for almost all of the planet detection methods, all of them, it becomes harder in order to detect them in the first place. So if you're just doing like a flat out search for these planets, you don't know that they exist from the get-go, you are more likely to find a larger or a more massive planet, all right? And then for the transit and the radial velocity techniques, as you go to larger distances between the planet and the star, it also becomes harder to find them. It's actually the opposite for direct imaging planets. So these few points out here, you might be wondering what those are, HR 8799. And it's actually more difficult for direct imaging to measure planets that are closer in. But for the vast majority of the planets that we have on this plot, it is harder going to the right. Okay, also, it is more difficult to find planets that are around more massive stars, okay? So if we think about the trend that we noted just from this raw plot earlier, that more massive stars maybe have more massive planets, that's actually a direct result of this detection bias, okay? So in order to actually understand what the underlying trend is, we have to understand our detection probability for our specific survey. You might hear someone refer to this as a completeness correction. Okay, so let's go a little bit more in detail about what exactly is a completeness correction. So one way that you can account for this and take a plot like that and actually make population level conclusions from it is by injecting signals into kind of the original level of data, passing it through your detection pipeline, and seeing how many pop up at the end. Okay, so the Kepler team did this. This is a necessary part of their mission because they wanted to measure the occurrence rate of planets of different radii and different periods, especially those that have Earth radius and Earth-like orbit. So here we have a whole bunch of points that were just injected into the Kepler data, and it was Jessie in particular did this work. She looked at whether or not she could detect these in the end, on the other end of the pipeline. So recovered is blue, not recovered is red. Then, after making this determination for all of the injected signals, what she did is she kind of collapsed all of this information and calculated this fraction of recovered signals as a function of effectively the signal to noise of the transit signal. This is for the Kepler data. So here the colors mean something different. So for the planets that are interior to 40-day orbits, that's the blue. Exterior, it's in the red. So you can see immediately here that it is much more difficult to measure, to find planets that are low signal-to-noise ratios. So what does the signal-to-noise ratio depend on for planetary systems? It depends on the radius of the planet. It depends on the radius of the star. It depends on the photometric noise of that star. And that's something that we had a good idea of, but stars actually surprised us once the Kepler mission launched, and stars are more noisy than we thought they were going in. So we actually found fewer planets at low signal-to-noise ratios than we were expecting. And it also depends on the period of the planet. So that's what you're seeing here, is that the recovery rate of these injected signals is lower at longer periods. It's harder to find longer period planets. Okay, another thing about this plot, this red curve was the theoretical detection limit that kind of the parameters of Kepler were designed off of. And you can see that we are not getting to that theoretical limit? What is creating that effect? Okay. The photometric noise from the star is correlated. There's red noise, and that makes it very difficult. This curve here was assuming Gaussian noise. It was assuming quote unquote white noise, and so it is harder to distinguish. This correlated structure of the noise can mimic transits when you fold and bend them in order to detect them in the first place. And so you're more likely to identify false alarms, signals that are not actually due to planets, when in the presence of correlated noise. Okay, so we will come back to this actually in a little bit. Okay, so once you actually do this completeness correction, these are the kind of results that we get, okay? So this plot shows us what the actual detected number is, and then how many planets were missed statistically based on this detection curve. And you can see how this changes as a function of planet radius. Like, as we just said, the signal to noise depends on that planet radius. And so because this completeness effect is dependent on the property that we are interested in getting the population distribution of, that means that we would have thought that this distribution looked something different than what it actually is. Okay, this is another, there's many papers published doing this completeness correction in the last 5 years or so. So Chris Burke, working closely with the Kepler team, did his own correction here. And then Courtney Dressing looked just at M-dwarf hosts and did her own correction. And here, it's not just looking at planet radius, but also planet period and what the occurrence rate of those planets are. Okay, so the kind of take home that I get from all of these plots, so if you kind of take this and then marginalize over this direction, you kind of make a histogram mentally about what the occurrence rate here looks like. My conclusion is that Earth-sized planets are actually more frequent, either as or more frequent than slightly larger planets. And you can see just the raw counts, that's not what the raw counts show. So you could, going back to this, if we look at this area of parameter space that all of these studies were looking at, these very small planets, you can see that the density of points drops off here compared to here. All right, so if you had just, that's another feature that we didn't actually note at the beginning, but we could have, you might have expected just based on this plot that you have fewer Earth-sized planets. Right. So this is a situation where we would have been misled. Okay, another point about this is that if we have different techniques, and we've heard about a whole range of planet detection techniques this week, all of them have different biases, all right? So here, thank you to Rachel Street for making this plot. Here we have the same parameter space. The points are from another planet population synthesis. The curves that you can see here correspond to different planet detection techniques. So in green, we have transits here. So this, the edge of this is basically the how long the transit survey went for, and then this is the kind of period-dependent completeness effect that we were just talking about. Then we have in kind of purple RVs, all right? So we can see that something somewhat similar to the transit survey, which is why there's such good synergy between radial velocities and transits. But we can also observe these systems from the ground for longer than Kepler did. So we have a longer time baseline. So we're pushing out to wider orbits. Okay, then astrometry, which we heard about yesterday. So there are a lot of kind of V-shaped curves that were being shown there. Then microlensing, especially via W first, is this huge blue region. So microlensing is really, really sensitive to the semi-major axes that are right around the snow line. And especially for the very low mass planets, this is the only planet detection method that's going to be able to get down there. All right, and then we finally have, direct imaging, which is currently all the way up there, but we hope to push down those contrast levels so we can find more Jupiter mass planets. Okay, so coming back here, so we talked about detection bias. Also, we don't just have to think about what planets are missing from this. We have to think about what systems completely are missing from this. And this comes from what stars did you select at the beginning of your survey to observe. So this is the selection bias. So it turns out that understanding your target stars is very important. And this is very effectively shown by the CTAS survey, that group. And so this is one of the kind of more recent population results to come out of the Kepler data. So we see here that there's a kind of large number of planets right around 2 to 2.5 Earth radii, and then a lot that's kind of less than 1.3 Earth radii, and not so many right in between. And so the question is what is driving this feature in this plot? By the way, this had not been noticed before. So I had a bunch of planet radius occurrence rate distributions before. None of them showed this valley right here. The reason why this valley showed up is because the typical uncertainty with new stellar parameters shrunk. And so all of a sudden they were able to resolve this valley here. So that's one reason why the target stars are important. If you look at this distribution in terms of the flux that is incident on the planet, then you see that this valley also extends in period. So the question is the gap produced during formation or by photoevaporative mass loss afterwards? So these two possible explanations for this gap have different period dependencies. So multiple people have looked at what the period dependence is of this gap, and it's looking like it might be photoevaporative mass loss. So that is exciting for our physical understanding of this population based on this data. Now, I want to tell a little bit of a story. There's actually a gap in the Kepler data before this. Why was it not published? I actually remember going to a Bay Area Exoplanet science meeting and sitting down with Tom Barclay and Jason Rowe. They were super excited. They were plotting new planet candidates to have just come out of the pipeline sometime around 2013, and they saw a bimodal distribution. And they knew that this physical interpretation was going to be very interesting. So they were like really excited and wanted to really understand what this gap was. The reason why it wasn't published then is because it was due to the distribution of the target star radii. All right, so to look at this a little bit more detail, so here I've plotted the Kepler magnitude of the star as a function of the star's effective temperature. This is the target star sample of Kepler. These are all the stars that were selected to be observed. You can see, very interestingly, there's this abrupt transition right around a Kepler magnitude of 14. What this means is that all of these stars, okay, so the color bar here is the minimum planet radius that it was detectable around that star based on its photometric noise. So you see here that there are more detectable, lower mass detectable planets around higher mass stars, and so larger radius stars, above a Kepler magnitude of 14. So this is where some of that peak of really small planets had been coming from in this bimodal distribution from 2013. And the slightly larger peak was coming from these fainter stars. where their radii were slightly smaller. So this is one of the, it's a little bit convoluted how your target star selection can actually lead to features in your population distribution that you were not expecting. All right. It took a little bit of thinking, but we figured out that bimodal distribution was produced by the target star. And so that's why you didn't see anything about that. By the way, the Fulton sample, it was taken from this area of the target star kind of parameter space. So they did not have to deal with this bimodal distribution. So what they found really is real. But I told this story just to kind of drive home how insidious some of these selection effects can actually be. You can really think that you found something real, but it's just what your distribution of star properties are. Okay, so going back to this, another factor that we have to think about. So we talked about what planets were missing, what systems were missing. Now we have to think about which planets that exist on this, that are present on this plot, don't actually exist. Right? These are the false positives. All right, coming back to this correlated noise issue. Correlated noise produces a lot of false alarms, and one scenario, one specific situation of this was Kepler 91b. All right, so here was the light curve of this star, and the transit suggestively plotted right here. If the model was not plotted, would you think that there was a transit there? No, I wouldn't either. And so the existence of this planet went back and forth a couple times in the literature. What happened with this paper is that they went out and got real velocities, and this planet does in fact exist. All right. So they were able to go back and do a Gaussian process regression analysis of the light curve, and with a simultaneous fit of the transit in order to get the radius of the planet. And so that's kind of what you see here in the kind of pinkish purplish. That's actually the Gaussian process regression of the light curve. Okay, so this also highlights some of the synergy, again, between transits and radial velocities. Here are the radial velocities. End of the debate, yes, this is definitely a planet, but if you're not able to get radial velocities for a certain star and its planet companion, you might be really worried about how many of these signals are actually due to variability in the star. Okay, and then we also have astrophysical false positives. So we were just talking about false alarms produced by correlated noise. I don't have a slide for this, but another really kind of annoying origin of false alarms are instrumental false alarms. So for Kepler in particular, there is this band structure that kind of rolls across the CCD, and it happens when Kepler had rotated every quarter. Certain CCDs have this rolling band structure more prominently than others, and so given the quarterly rotation, this popped up every year, and so it was one of the most common false alarms for Earth-sized planets in Earth-like orbits. And it's one of the reasons why there are just so few G-type star habitable zone planets to come out of Kepler. All right, but there are also astrophysical false positives. So you heard from Tim Morton earlier this week, and you've gotten to play around a little bit with Vespa, hopefully. So this is one of the first publications he put out to kind of develop, this became Vespa. So he considered various scenarios, astrophysical scenarios for reproducing a planet-like transit shape. In particular, he looked at three aspects of the transit light curve: the depth of the transit, the duration of the transit, and then also kind of the shape of the ingress and egress. And so what he did was he simulated a population of these astrophysical false positives that could fit those three parameters in the observed light curve. And so the proportion of parameters that can actually reproduce the planet light curve is in blue. So here we have background eclipsing binaries. So what you should think of there is we have the target star. This is what the star that we want to find planets around. Then we have just by chance nearby superimposed on the sky a background eclipsing binary. And so it turns out because so much of this parameter space could reproduce a planetary transit, background eclipsing binaries are very problematic for transit surveys. Just an example. He also looked at others, hierarchical eclipsing binaries. So here we have a eclipsing binary that's actually physically bound to the target star that we want to find planet around. And so there is still a solid amount of parameter space that could reproduce that. Then over here we have just regular old eclipsing binaries. So if the secondary star is small and cool enough, then it would produce a depth that is similar. There's some fraction here. And then there's also the issue of just incorrectly measuring the planet radii if we have a blend here. So this background star, it doesn't matter whether it's bound or not, it dilutes the transit. And so the transit depth that we measure is too small given the size of the planet. We would think the planet was smaller than it actually is. And that also happens quite a lot of the time. So these are also, these false positive scenarios are something that you have to keep in mind as well when you're thinking about doing population analyses. So Jen Yi yesterday talked a little bit about what these false positives could be in terms of microlensing, right? So she went in detail through all of the microlensing light curves, talked about which ones that could be just two stars would produce a light curve that might look like there was a planet there. So this kind of thing, and then for direct imaging, right, you have to do this kind of astrometric following in order to make sure that, that Quinn talked about just this morning, in order to make sure that the planet is co-located and actually physically bound to the star. So every single detection method has these kind of things that you have to think about. Okay, and then finally, one last consideration is how do we need to improve our methodology for improving our understanding of planet populations. So this is what I work on a lot, is the methodology behind analyzing planet populations. So one point here that I want to make is that improved methods can actually significantly change results. So I talked a little bit about occurrence rates earlier. So sometimes what people like to do is to plot occurrence rates as a function of orbital period or semi-major axis, and then either planet radius or planet mass here. So this is work done by Danley Su at Penn State, and what he did is he realized that the inverse detection efficiency method, one way that you in detail correct for this completeness effect, is actually biased. It's biased so that if you have a non-detection, you will underestimate the rate. And if you have a planet that is just slightly too large, you will also underestimate the planet occurrence rate. So it's not an effect that just balances itself out. And so what he did is he implemented an approximate Bayesian computation algorithm that corrects for that the deficiencies of the inverse detection efficiency method. And this is what he found as compared to that method. So the color bar is not actually the occurrence rate, it's showing the difference between the inverse detection efficiency method, that's a mouthful, and the ABC method here. And so in particular, what he found is that in this crucial area of parameter space where we really want to understand what the occurrence rate of Earth-sized planets on Earth-like orbits are, we are underestimating this by just using a bias method, okay? So actually looking at the methodology and at the statistical techniques that you use and doing something that is warranted to be a little bit more sophisticated can actually help us understand the population better, okay? Another point here that I want to make about kind of improving methodology is thinking about distributions instead of lines. When you're thinking about trends in the population, often, especially for exoplanets, there's enormous diversity of what exoplanet properties are. And so instead of just kind of fitting lines and finding the average trend, what you might want to do is actually to think about what the distribution is. So you're more fully characterizing the population itself. So this is an example from my work about where I did this. So this is the mass-radius relation. I was interested in predicting exoplanet masses based on their radii. Okay, and so if you were just to fit one kind of line here to look at the trend, that's what the blue line here would be. But I was interested in the intrinsic scatter of this relationship. So that intrinsic scatter is noted here, okay, in the shaded region. So what this does physically is it allows for a distribution of composition at any given radius, okay? If we just fit one line, you're forcing your planets to have one composition at that size. And we know from the data that this is not actually the case. Okay, so it helps us understand the population better. In particular, the method that I used, hierarchical Bayesian modeling, allows us to distinguish between the scatter that is due to measurement uncertainty, and you can see that the error bars here are quite large, all right? So there was a question of how much of the scatter in this space was actually just due to measurement uncertainty versus astrophysical scatter. So planets actually are composed of different compositions. And what I found is that the astrophysical scatter is very much there. Okay, right. So this really helps us understand the physics of the planets by kind of looking at the distribution of compositions. Okay, so looking towards the future, where is planet populations going? Okay, so this is a plot of all of the current and future NASA missions and some of their ground-based facilities. So so I went to EPRV, so Peter mentioned this. It stands for Extremely Precise Radial Velocities. It's a workshop that happens every 2 years or so. And at the previous one, there were 23 ground-based radial velocity instruments that were either working currently or being built in order to do radial velocity measurements of planets. But there's no way that I can put them all here. But you can get a sense of the kind of things that the radial velocity kind of technique can do. Also, it's worth thinking about the next generation of ground-based telescopes. Okay, so I have categorized these when you're thinking about populations. I've categorized these in terms of some of the dominant planet detection methods that they will use. Because of the point that we made at the very beginning, that the detection bias and completeness depends on the survey, the detection technique that you use. Okay, so starting with current or past missions for the transit missions, there was Kepler and Corot. A lot of the radial velocity follow-up for that happened at Keck. In addition to all of those ground-based facilities as well. Okay, then we have some, I also wasn't able to put down all of the direct imaging surveys that have happened, but there's been some that have happened at the LBT. And okay, so Hubble, so we heard about astrometry yesterday. Hubble has also been very important for understanding exoplanet atmospheres. So I added atmospheres here as kind of a future way that exoplanet populations, and very exciting way that exoplanet populations are going to start to become important. And then also a lot of atmospheres with Spitzer. So this is kind of current day / past missions that are happening. People are getting data right now, or will very soon be getting data, especially as it relates to planets, TESS, CHAOS, and Gaia. Then we also have NUID and JWST. These are currently being built. Okay, and then kind of facilities that are chosen or very close to being chosen, and the very future observatories that are going to, that are the subject of the decadal survey that are coming up. So if you have not familiarized yourself with what the capabilities of these are, Peter mentioned LUVOIR and HABEX, but Origins is also going to be really exciting for atmospheres. Then go ahead and kind of look up the materials that these teams have online already. So basically, all of the things that are coming in the future have possibilities for exoplanet populations. I particularly am excited about populations of exoplanet atmospheres. So we're already starting to get to this with HST data, but there's going to be lots to consider for JWST, Origin Space Telescope, about how we select our targets and what the presence of clouds are doing. And then in the future, we're going to have to do a lot of work to synthesize all of these results from many different surveys. So a really great first stab of this was done by Christian Plantin and Scott Gowdy, kind of looking at the mass and semi-major axis distribution across multiple surveys. All right, so to conclude, I'll leave you with this plot again. A big goal, a lot of work to happen in the future with exoplanet populations will be synthesizing all of this into one exoplanet census. So this is going to involve different survey completeness, different observables. I didn't even really talk about that, different stellar samples, thinking about different false positive scenarios, and then just improving our analysis techniques for populations to begin with. So to leave you with a thought, obtaining the exoplanetary census is a really significant endeavor, and there's plenty of opportunity for all of you to contribute. Thank you. So, yes, thank you. So the question was about the Fulton gap. Couldn't that turn out to be a product of statistical biases? So I talked about how it was not a result of the selection bias. In terms of detection bias, that area, he corrected for that in his analysis. So he took care of that. Otherwise, it might be a difference in the kinds of stars. Maybe there's an activity level situation there, but you would have to really construct kind of edge case scenario for explaining that gap through some sort of statistical bias. So he did that paper was high quality. He did a lot of good work there. Yep.
Okay, so thanks again.
Thank you.